Adding additional independent variables to a multivariate regression will always increase the R-squared, aka coefficient of determination, but that doesn't tell us that the model is necessarily a better fit. And that's why we really should use the adjusted R-squared. In order to illustrate the adjusted R-squared, I'll use the example from Stock and Watson Chapter 6 that is assigned to FRM candidates. And it's a multivariate regression as opposed to univariate. Multivariate meaning we have two or more independent variables. And in this example, the dependent is student test scores. So we're regressing the dependent to student test scores on two independent variables, the student-teacher ratio in the classroom, denoted STR, and also the percentage of English learners in the school district, denoted PCTEL. And to get the regression output, I've just used Excel's linest array function, and it's going to give me 5 rows, and the number of columns is going to correspond to the number of coefficients that are estimated in the regression. I have 1, 2, 3 columns. That will match the number of variables that are in the regression. Because you'll notice here I have 2 independent variables plus 1 dependent. I always have 1 dependent. That's 3 variables, and it corresponds to 3 columns, which is 3 coefficients. I'm estimating a partial slope coefficient here, a partial slope coefficient here, and also the intercept coefficient. And so the first row gives me the regression coefficients. The second row gives me the standard errors associated with the respective regression coefficients. Those standard errors are also standard deviations. And then in the third, fourth, and fifth row, I get, just like I get in the univariate regression, I get measures of goodness of fit in general. Starting with right here, the one that I'm interested in, 0.426, you can see over here in the legend, is the R-squared. I think most people call it the R-squared. It also has a longer name, the coefficient of determination. And here I'm getting about 42.6%, you can see. We can interpret that as approximately 42.6% of the variation in our dependent, or in other words, the variation in student test scores, can be explained by variation in classroom student-teacher ratios and district, the percentage of English learners in the district. So I think that's a pretty good R-squared. Some people expect to see higher R-squareds. However, it is an unadjusted R-squared. Wasn't so relevant in the univariate, but becomes relevant in the multivariate. And why is that? Well, that is because if I added another independent variable, which I'm not going to do, I will necessarily increase the R-squared. If my goal is to increase the unadjusted R-squared, all I need to do is add independent variables. The unadjusted R-squared will always increase as we add new independent variables. The problem is that that doesn't necessarily make the model a better fit. And that's the point of the adjusted R-squared. And so how do we get that? Well, it's not too difficult, really. It's just not built into the output here. What I have in blue here is the regression formula in a more conventional format. So it repeats, you can see here, test score, intercept plus my 2 slope coefficients, and then below the coefficients I have the standard errors, so that repeats from the table. And then I have the unadjusted R-squared and the standard error, the regression, which is also right here. So N here is the number of observations in my data sample. And I mentioned in a previous video, a tip, that we can take the degrees of freedom, which you can see here are 417, and that's labeled DF. We can take the degrees of freedom and add the number of columns, and we'll get the sample size N. In this case, 417 plus 1, 2, 3 is 420, and that is the size of our sample. So N equals 420 observations. The variable K here is the number of regressors, and in my spreadsheet, which I'll upload and has dynamic labels here, regressors is a synonym. It's the word that's used in Stock and Watson for what I prefer to call independent variables. So we have 2 independent variables or 2 regressors, and that's K. Here I have the standard error of the regression and the total sum of squares. The total sum of squares is, as you probably know, just the sum of the explained sum of squares here and the sum of the squared residuals here. So that happens to be 152,110. These are not intuitive units because they're similar. They are in fact the same units as the variance would be. So they're in squared units, not themselves lending to an intuition. And so the unadjusted R squared, which we already know from the table, is 0.4264, is the explained sum of squares, which is here, 64,864, divided by the total sum of squares, which is not directly on the line S because it would be redundant information. It's just the sum of the two. So you can see right here, the denominator there is the explained sum of squares plus the sum of squared residuals, and we're getting the 42.64% as the unadjusted R squared. So this is the number that will necessarily increase if we add independent variables. So then we're in a position to compute the adjusted R squared, and we just need the adjustment factor. So the adjustment factor here is n minus 1 divided by n minus k minus 1, which is also n minus 1 divided by the degrees of freedom. And in our case, you can see that's 419 divided by 417. And so this adjustment factor will always be greater than 1.0, such that the adjusted R squared is always going to be less than the unadjusted R squared, because what we're going to do for the adjusted R squared is take 1 minus the adjustment factor here times the sum of squared residuals divided by the total sum of squares. And you'll notice that when f is equal to 1, we're getting the formula that we get just for the unadjusted R squared. So the adjustment factor itself, always being greater than 1, is going to lead to a slightly greater subtraction and an adjusted R squared that will necessarily be less than the unadjusted R squared. And so you can see here in my formula, it rounds to 1, but my adjustment factor is 1.00480. It's not very much higher than 1, but my adjusted R squared is dropping down to 0.4237 to incorporate the fact that I have an additional independent variable on top of the first independent variable, and to account for the goodness of fit, so that I can say three things about this adjusted R squared. And the first is that what I've already said, our adjustment factor here will always be greater than 1. And so the adjusted R squared will always be less than the unadjusted R squared. And that's because, secondly, this adjusted R squared has two influences, right? The factor here will always be greater than 1, but this ratio here, as we add another variable, will always have an opposite effect. As we add an additional variable, the sum of squared residuals will go necessarily down, but the factor will go up. So we have offsetting effects, meaning that it's unclear as to what will be the impact of an adjusted R squared as we add independent variables. And then thirdly, it happens to be the case that the adjusted R squared could be negative. So I hope that's helpful. Thanks.